right, so this will be the last shape we'll do before Wednesday. This is going to be an infinite plane of charge. So just like our line of charge or our ring of charge, we have this definition of eta that defines for us that we have this total charge, Q, big Q, for the entire surface. And in this case, because we are doing a plane of charge, that's that Q into that entire surface area. We use eta, some people use sigma. Don't panic if you see it in different ways. It's just describing the exact same thing. And I want to remind you that we start with everything in terms of our electric field. So the fundamental definition of that is the electrostatic constant, the charge causing the electric field divided by the distance away that we are measuring that E field. Now, even though I've drawn this as a small, just a reminder, this is going to go from negative infinity to an infinity, so it's an infinite plane. This does do something for us, however, that is a little bit disconcerting in that we are now working in 3 dimensions. So here's my plane, and I'm picking a point out here. So this thing here, that would be my Z plane, and I can name this my XY plane. You can rotate that any way you want. It doesn't much matter, but that's how we're going to define it, that I have a Y plane and an X plane. Let me do them in the same color. And then this is going to be some spot Z away. We'll just stick with Z. And so just like what we've done before, we're going to pick out some small surface element, like one of the little charges, a teeny, teeny, tiny little dx and a teeny, teeny, tiny little dy. And we are going to see what the electric field is from that point. So my R is still just coming out here, even though it's a 3-dimensional thing. Kind of connecting like that. And one of the first steps that we can do if we want, we can jump into deciding how do we define R. Okay, so let's see. Ooh, we have this 3-dimensional plane. Let's see what's happening here. I have this distance coming out in the X, and I have this distance coming up in the Y. So if I look at this piece and this piece, they're connected from the origin by like that. Whoops, like that. So using Pythagorean, I can define that distance to get that piece of the right triangle, and that would be defined as, I need more space, the square root of then x squared plus y squared. And this big thing R then, well, it's still just Pythagorean, so the square root of my components squared, and I'm going to write it here. So R is going to be the square root of, what do I have? I have the square root of x squared plus y squared, that quantity squared, plus z squared. And then I look at that square root of a square of a square root, rather, is just going to give me then, that simplifies down to x squared plus y squared plus z squared. Okay, so we've defined our R. Now the next thing is to go ahead and put that in there. And so we know that E then is going to be KQ over R squared, so the square root is going to go away. And I'm left with x squared plus y squared plus z squared. Sweet. All right, now we know we're doing a collection of charges, so we're going to have to sum up all my teeny, teeny, tiny little dq's and all of my dx's and dy's and integrate over that. So I do know that I'm going to end up with some sort of area change. So I guess the next thing I could do is look at my eta. So what is that going to be? That's going to give me, for this whole surface, some sort of change in Q over an area, or a change in area. Well, this is an xy plane, so it's going to be some little piece of my x times a little piece of my y. It'll give me that tiny little surface element. And again, let's just solve this for dq. So dq then is going to equal eta times my area element, dx dy. Cool. So then I kind of feel like I can do this. I don't want to do that. I can rewrite that I'm going to have some sort of dE is going to equal my k dq over my r squared dx dy. And then I can make that substitution. That my dE then is going to equal my k, making the substitution for my eta. So eta dx dy divided by, what did I just do? Took what I wrote just above it instead of putting in my r squared. Sorry about that. So let's write that the correct thing. That's my r squared, x squared plus y squared plus z squared. And there we go. X squared plus y squared plus z squared. Cool. Okay, eta dx. Okay, well, we're getting there. Now let's think in terms of what pieces are going to go away. So what's nice with all of these things is that we are going to have symmetry components. What's harder to see on here is that we're essentially repeating this process here. So this is kind of looking flat on to my z. If I called this direction my z direction, then I'm going to have the same thing where my x component or my z component is going to survive and my y components are going to cancel. And the same thing holds true here. It's just harder to see because it's three-dimensional, and drawing in three-dimensional is hard enough to make that visually apparent, especially when you're trying to do it on a computer. Okay, so let's just draw this out. So I'm going to have then some sort of z component coming out. And we're going to give up. That's going to be close enough. Just move it back here somehow. There we go. Of course, you took my dot too. So we want that piece. Now remember, from everything else that we've done, defining that piece, what am I going to have? If I think of this as the electric field continuing on down, something like this. Excuse me, I cannot draw in 3 dimensions. That this angle here is the exact same as this angle here. And so my z component is again going to be, well, it's going to be touching the z side, so I'm going to have something like cosine of theta equals adjacent z over my hypotenuse. Well, I've defined my hypotenuse already in terms of my r. So I have, we'll write it as x squared plus y squared plus z squared, whoosh, to the 1/2. Okay, now we've done enough of these. I'm going to skip the step of rewriting the to the 1/2 because I'm going to have 1/2 times my x squared plus my y squared plus my z squared to the 1. And so that's going to give me my dEz k eta dx dy over x squared plus y squared plus z squared to the 3/2. And then times my z. So this gives me everything in a z hat direction. Cool. Let's see, are we ready to integrate? I kind of feel like we are. So we can page down some. And I'm going to do the same thing. Let's go ahead and pull out. I'm going to move over a little bit here. Let's go ahead and pull out our constants. So here's my dEz. It's going to equal, let's see, what is constant here? I have a k is constant. I have an eta is constant. And z, remember, is just the distance away, so that's constant as well. And then that's going to give me this double integral, which terrifies so many people. But let's see that that's not so bad. dx dy over x squared plus y squared plus z squared to the 3/2. All right. Now with our double integrals, I'm going to have like one is like x equals and the other is going to be y. It doesn't matter which order. As things get uglier down the road, and not in this class, like in next year and the year after, then picking the order will make life easier and you can get into how to choose that then. But in this particular case, just choose one. And that's what I'm going to do. I'm going to integrate my dE. We can go ahead and write that now. It's just going to be the E total in the Z. It's going to equal K eta Z times the integral. Seeing as I wrote X here, I will go ahead and start with X dx times the integral for my y and my dy over this ugly mess, plus y squared plus z squared. Now there's something we can do here. I can look this up to see what this integral is, and it's no problem, but one of the things that will make this easier is I can look at this and say, what's going to stay constant in this? Well, my x squared is and my z squared is. So I can redefine that. I can make a new variable and go, so let's make a squared equal x squared plus z squared. And rewrite this integral. And that's going to make sense in a second. It's going to be easier to rewrite. It's okay. E to z times the integral dx times the integral of dy over a squared plus y squared. Yeah, making sure I didn't mess that up. 3/2. Perfect. Now we're going from negative infinity to infinity, but one of the things that we can do to make life easier is to go from 0 to infinity. And if I'm going to do that, then I just multiply my integral by 2. So let's pull that out here. There's my 2. And now we can integrate this thing. If you remember from the other video, what does that come out to? 2k eta z times the integral dx times, let's see, this integral is going to be, what's going to happen, I'm going to get a y up top, and a squared pops out. I get a squared plus y squared, and the 3/2 becomes 1/2. And that's evaluated from 0 to infinity. Okay. Now, don't know if you have gotten this far yet in your calculus class. Let's take a look at this thing as far as how it relates to integrating with respect to infinity. I'm going to erase this thing. What do we have? If I evaluated infinity, I'm going to have like infinity over a squared times a squared plus infinity squared to the 1/2. The lower limit, that's not so bad because that's just, I'm plugging in 0 to y, so that's just going to be minus 0. So this is the thing that we need to focus on. So let's think about this for a second. So what is this? This is like this ginormously large number, and I'm squaring it. So I have a ginormously large number plus something that's not ginormously large. So we're going to assume that a is nowhere near infinity, so infinity is much, 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 much larger than a. And if that's the case, when I square them, that means a is going to be even that much smaller compared to infinity. So one of the things I can do is kind of look at the limit of this thing, and I realize that a is going to be really diminished as far as that addition goes. This one here we can't ignore. So what is that going to come out to then? Well, if a squared is really small, well, the square root of something squared gives me what? I get like infinity over infinity times 1 over, I don't know why that e keeps popping up, 1 over a squared. Any number, no matter how big it is, divided by itself, or you can do the math hoo-ha, let's take a formal limit, whatever makes you happy. This whole thing here is going to go to 1. So this ugliness here simplifies down nicely, and I'm going to get that my e in the z equals 2k eta z, the integral dx, times, let's see, what do we come up with then? We have 1 over a squared, and that's it. Now, before I ignore that a squared, let's remind ourselves what a squared equals. A squared is x squared plus z squared. So I'm going to have this equals 2k eta z times the integral of dx over x squared plus z squared. Yep, just wanted to double check, and that quantity is squared. Cool. Now we're going to have the same limits here. I'm going to have I'm sorry, I just realized something. Yep. A squared equals that. Check that. I was double squaring something. There we go. So what did I do? When I have 1 over a squared, I've defined a squared as equaling x squared plus z squared, so we're not squaring it. We already know what that equals. Okay, fix the boo-boo. Same thing with our limits. I want to go from 0 to infinity to make my life easier. And in doing so, that means I need to double that. So let's rewrite that neatly. So 2 times 2, that brings out the 4k eta z. And then we have the integral from 0 to infinity of dx divided by x squared plus z squared. So this is a fun one, and I have my little cheat sheet so I can remember what that integral is. In this, you can look it up on an integral table. And by the way, I would not expect you to be able to deduce these by hand just yet. So using an integral table or Wolfram Alpha or any one of those to get you your indefinite integral is just fine right now. Later on, we'll worry about having to do those things by hand. But I look this up on a table and I find out that 4k eta z times, and I get 1/2 times the arctan, I'm sorry, 1 over z times the arctan of y over z, of x over z, sorry. And that's evaluated from 0 to infinity. Okay, so let's think about this. What's tangent? Let's draw a triangle. Oh, you're not going to give me a right triangle. Never mind. It's going to be fancy. We won't do it. There we go. Straight out triangle. So if this is my theta, arctan, opposite over hypotenuse, if theta equals 0, so if I evaluate this thing at 0, then that means I have no sides, so this thing would be 0. If theta equals infinity, another way of thinking about that, what I'm saying, I'm opening this thing up as big as I can get it. So if I'm doing that, then that means I am at 90 degrees, so this expression will evaluate to pi over 2. So I'll get 4k eta z times 1 over z times pi over 2, then minus 0. Now let's simplify. What do I get? My z's cancel out, and I get that my e in the z equals 4k eta times pi. I don't know what, oh, my eta just got all sorts of fancy. Let me clean that up, I'm sorry. 4k eta, there we go, times pi divided by 2. Now if you look in your book or elsewhere, everybody is very fond of using this, that k equals 1 over 4 pi epsilon naught. So we can make that substitution if we want. That e and the z, or the e total, is going to be 4 eta. Why can I not do an eta? It becomes something all on its own. So 4 eta pi over 2 times 4 is 8 pi epsilon naught. This is why you're looking in your book and you're like, wait, it was like, that cancels out and that goes to a 2, and the pi's cancel out. Then you see this handy dandy equation that's eta over 2 epsilon naught. Boom. That is where that darn thing comes from. Is all this work that we just did. But notice we followed all the same approaches that we've done before. And yeah, I don't always go in the same order, but more or less letting the Coulomb's equation guide you. You know, define for yourself how can you mathematically describe your R, and then take a look and ask yourself what components are going to cancel out. So when we're doing any of these sheets, you're always going to have symmetry involved. So just decide. And you're going to notice a pattern evolving there. The other pattern that you're going to notice is this whole thing where everything ends up over to the 3 halves. That's just geometry is going to get us there. So you'll see that repeating a lot. Then after we do that, it's doing our actual integral. So when you get it down to here, and we're ready to integrate, well, now you can pull out any integration table or MATLAB or whatever. Don't worry, I will tell you when it's time to start doing these things by hand. I realize enough of you aren't far enough into it yet. So you look those things up. As far as your infinities divided by infinities, it's a little hand-wavy, I admit. But once you get into limits, it'll make a little bit more sense. It essentially boils down, you're going to get the same darn answer. And then this arctangent thing, you can always look up arctangent of infinity and to see what those values are. Try to have it make some intuitive sense as far as how or where those things come from. It'll help you feel less confused as we move on. But it all follows the same thing. So what we're going to do on Wednesday then is do a disk of charge and a plate of charge, or 2 parallel plates rather, because that is what we're going to use in our next section when we start getting into electronics. So we're going to pull all these pieces together. All right, have a good day.